And this is a very important playlist because it has many applications for a future of artificial intelligence, such as neural Turing machine and those things. So I start from basic stuff, from deterministic, finite, automata, regular languages, and then context free languages, and then context sensitive languages, and then Turing, and then non Turing. So I start from basic things to more complex things. So I start from very basic, very constrained things, and I then relax everything, and then I go through more general languages. And you will see how you can implement it in computer science using just stack and very simple things such as queue, stack, and like that. So these are the books that I have combined the materials of all of these books so that you see the bigger picture, so that you understand how you should look at those things. For example, if you look at your brain, if you look at your DNA inside your body, it has a language: A C T G A C C T T, and you see, if you want to understand these things, which is called DNA computing, you need to understand theory of computation, and in your body, it is done every second. There is a computation in your body, and you need to understand the mechanism behind it. And nowadays we have recurrent neural networks with the stack. I have a playlist, RNN with the stack. And if you want to understand that playlist, it is better to understand this playlist, which is about basic stuff, theory of computation, everything that a computer scientist should learn. And so let's talk about this. So these are my books. These are the books, my references, but these are also important. But they are very modern things. They are also related to formal language theory, and also to, even it is highly related to symbolic dynamics and dynamical systems. Shift spaces and those things. So let's start with deterministic finite automata. We have input tape, for example, A, B. Think about it as your DNA. It's just a sequence. And so A, B, A, B, A, and then we are reading from that. So you have a controller like this. For example, in the article Neural Turing Machine that I explained, you have a controller that says when you go from one state to the another state, when you go to the other state, then the next step you go to the another state. So there is a state machine, you go to another state if something happens. For example, if you read A, it goes to another state. If you read B, it goes to another state. And so you have a couple of states, and this is the dynamics of that. So this is a controller that says how it goes from one state to the another state when an input arrives. So this process is repeated again and again. A symbol is read, the reading head moves to the right, and the state of the finite control changes. Eventually, the reading head reaches the end of the input stream. The automaton is a singular word. The plural word is automata. Automata is the plural word. Then indicates its approval or disapproval of what it has read by the state it is in at the end. If it winds up in one of the set of final states, the input is considered to be accepted. For example, we go from Q state to Q2 state if the input is A, and we go to Q3 state if the input is 3. But if I have double circle, it means Q3 is finite. So A, B is part of my language. Or, for example, any other path. And also it may have many loops. So let's define this deterministic finite automaton, which is the simplest thing that you can imagine, the simplest language that you can imagine, you can generate it by this finite automaton. So we have K is a finite set of states. You go from one state to the another state. Just like in your brain, there are some neurons that are active at each instant of time. So at one state you go to another state. I mean, in the other state, another set of neurons are turned on, and so on. So you see, you can also analyze the neural networks of your brain as well using this. So we have a finite set of states, K. We have sigma, which is an alphabet. Alphabet could be A, B, or in genetic, we call it some molecules, some T, C, A, G, some enzymes, some chemicals. When they're arranged in a particular sequence, then, so this is a kind of a string. So let's call it this our string. And these are important because your DNA creates RNA and RNA creates protein. So if the sequence is not correct, then the protein will not be created inside your body. So S is an initial state because just like a dynamical system, a differential equation, you start from some initial condition, and this is the path. So this is the path. If it is time variant, you have a different, or you have a control, like control systems, you can have different paths. But the initial condition, if the initial condition varies, the dynamics varies, or eventually they may reach together. So if this is one initial condition, S1 and S2, the trajectory changes. So I am talking about the thing, you can think about it as a discrete dynamical system. Instead of this continuous line, you can have discrete dynamicals. You can think about it like that. We call it symbolic dynamics. It's an old topic, goes to ergodic theory and those things, but you will see that the future of artificial intelligence is highly dependent on these things that we knew 100 years ago. So what is yield? Yield is this operator the binary relation holds between two configurations. And this is, for example, a configuration of a deterministic finite automaton is any element of your state, time, your that sequence. For example, this example, you have a set of states, Q0 and Q1. For example, you have A and B, and you start from some Q0, some states, you go to another states. For example, if you are in Q0 and you have A, you stay in Q0, and you see these simple examples. And so if M is given, the input A, B, B, A, its initial configuration is Q0, A, B, B, A. For example, you're in state Q0, then you understand that which rule you can use. For example, you can use Q0, A, it means Q0. When it says Q0, so when it says A, it says Q0. And then when Q0 and B, it becomes Q1. So sometimes you go to Q1. And Q1, if it sees B, Q1 if it sees B, Q1 if it sees B, it goes to Q0. So it goes here if it sees B. So that's why Q0B it becomes Q0. And the next input arrives here. Now Q0A, it goes to, you can use this law, this rule. All of these, rule 1, rule 2, rule 3, rule 4. So now I use rule 1 to go to this here. But this is, we call this empty state. And so it means that you have reached the final state, Q0. So we understand that this is inside your language. This is accepted. We use the term accepted by the language. And this is another example that we have a set of states, but now we have 4 states, Q2 and Q3. So we have 4 states. So depending of the input, you go to different state depending on the input. But this is a regular, it just needs an input. It doesn't look at the stack, right? But you will see that some languages are more general. You need context-free grammar, and you should implement it with push-down automaton. But in this part, you assume that we have a regular language. It means that the irregular language, it means you can implement it with just a simple finite state machine. And this is another example. Whenever you see double circle, we mean that it is an acceptable state. So let's generate something. For example, you start from here, B, and then A, and then B, and then B. So this is accepted. So this is part of a language.